Assalamu alaikum. Welcome to the next class. In this class, we'll be doing the equivalent circuit of a real transformer. Before this class, we discussed about the ideal transformer and what are the different assumptions that we make for a transformer to be ideal. So here we're relaxing those assumptions and we want to see what are the different things that we have to take into consideration while dealing with the actual transformer. So here is a transformer which we assume it is on load, and practically we assume that the transformer winding resistance is zero, sorry, ideally, but practically there is some resistance. So when we have to deal with the practical transformer, we have to consider that resistance, because that resistance leads to the copper loss, that is I square R losses, and due to this we can determine how efficient a transformer is. So one more thing, that while major part of the flux is confined to the core as a mutual flux, that is phi, linking both primary and secondary, there will be a small amount of flux that will leak, or there will leakage flux from on the primary side as well as on the secondary side, whose path will be mostly through the air. If the flux produced by the primary is phi, let's call that as phi p, the flux that it that flux phi p will be divided in two parts. One will be phi m, which will be the mutual that will link this coil, and there will be phi lp, which will go through the air and again goes to this coil. It will not link to this coil. So this will be the leakage flux of the primary. So on the reaction of this flux phi, it will try to produce the flux in the upward direction, so that, but that flux will also have some leakage flux phi ls. That means this flux will have it is the actual flux. It will produce the actual flux of, let's say, phi s. So that phi s will be divided into two parts, that is phi m and phi ls. So by taking these two equations into mind, we will do the analysis for this case. So here we're assuming for the simplicity that whole primary is on the left side of the transformer core, and whole secondary is the right side of the transformer core. It is for the simplicity of the understanding, we're assuming this here, but practically you know that half of the primary and secondary are on this side and half of the primary secondary are on this side. So there will be a flux phi lp that is caused by actually the mmf produced in the primary winding, that is N1 and I1, that is the current in the primary winding. It links primary winding itself as phi ls caused, and the phi ls, that is the leakage flux of the secondary winding produced by the mmf N2 and I2. They cause the self linkage of the two windings. That is the flux which only links. This links only to the primary winding. This links only to the secondary winding. So in earlier, we know that the half of the primary is on the one core and half of the primary is on the secondary core. Same is the case for the secondary winding. So that is actually done to decrease this value, that is the leakage flux. But even if we do that, we have some leakage flux. We have minimized the leakage, but we have not eliminated the leakage. Let us first discuss about the inductance, because we are arriving on the inductance. L is equal to lambda by I, where lambda is the total number of flux linkage, that is n phi divided by I. Let us multiply by n and n on numerator as well as on denominator to be equal to n square phi divided by n into I. So this Ni is the mmf, total mmf, and we know that for a magnetic circuit whose reluctance is given by R, this Ni will be given by phi into R. So this phi and phi will cancel out to be equal to n square by this R, where R is the reluctance of the magnetic circuit. So I can replace this n by this psi, where psi is 1 by R, that's the permeance of the magnetic circuit. Then that means this inductance is equal to n square into psi. Again, the flux equation on the primary side will be equal to phi p is equal to phi m plus phi lp. That's what I have just told you. This is phi p is equal to phi lp plus phi m. phi p is the total primary flux, phi m is the flux component linking both primary and secondary coil, that's the mutual flux, and phi lp is the primary leakage flux. Similarly, for the secondary side, we have phi s is equal to phi m plus phi ls, where phi s is the total secondary flux, phi m is the flux component linking both primary and secondary coils, and phi ls is the secondary leakage flux. So with the division of the primary and the secondary mutual and leakage components, Faraday's laws of primary circuit can be expressed as. So that means this equation can be converted to voltage by the Faraday's law of induction. That is Vp is equal to N P d phi p by dt. So that is this value. So this is equal to where phi p is equal to phi m plus phi lp. When you differentiate it, it will be equal to np d phi m by dt plus np d phi lp by dt. So this equation, or you can directly differentiate this. This will be equal to, by multiplying np first and then differentiating, it will be equal to np d phi p by dt is equal to np d phi m by dt plus np d phi lp by dt. So this is the equation Vp. That's what here it is written as. This is, let us say, EPT, that is the EMF produced. This is the input voltage, and this is the ELP. We can say this will be the voltage drop due to this flux leakage. So on the secondary side, we have the same sort of equation. Vs is equal to ns d phi s by dt, where when we replace this by phi m plus phi ls, it will be equal to ns d phi m by dt plus ns d phi ls by dt. So this produces the voltage, secondary side voltage, that is induced on the secondary side, and this is the voltage drop due to the leakage flux. One more thing, in general, we know that phi is equal to Ni by R, that is mm by reluctance, or when you replace this one by R by psi, it will be equal to Ni into psi. So phi Lp will be equal to, that is psi, that's Np into Ip, because this is produced by ultimately by the primary current and multiplied by the primary number of turns. Similarly, phi Ls will be equal to psi Ns and Is, since the reluctance of air in here and here is same, so that's why we have written the same psi over here. So writing these equations, that's for this case, that is ELPT, that is the voltage that is induced due to the we can say voltage drop due to the flux leakage. It will be equal to NP d phi lp by dt. So NP is as it is, so d by dt is as it is, and for phi lp we have psi into NP into Ip. So when you take this NP outside, it will be n square p psi into di by dp, and we know that this equation we have just derived, it will be equal to inductance, and for NP it will be equal to inductance of the primary circuit. So when you draw it into the, we can say, phasor form, it will be equal to j omega Ip into Lp. So, or we can say j, where omega into Lp will be x, so jx into Ip. So this is, we can say, the inductive voltage drop. This flux leakage flux will, because finally it will not link to the secondary winding, there will be an induced EMF which will be definitely less as compared to the without leakage. So since there is leakage, that leakage produces some voltage drop. That voltage drop is inductive in nature. That's what we have derived over here. So where Lp is equal to n square psi is modeled as a self-inductance of the primary winding due to the leakage flux, and hence because of this leakage it is known as leakage inductance. And you will always see that transform has a leakage inductance. You will not see self or any types of leakage. You will always see, because this is quite related to the leakage flux. Similarly, ELS T, that is equal to Ls dis by dt, is equal to j omega is Ls. So this will also be the voltage drop in the inductive voltage drop in the secondary circuit. So while Ls is equal to n square psi is modeled as the self-inductance of the primary winding due to the leakage flux, and this is also known as leakage inductance of the secondary side. So when we model them in terms of practical, or we can say electrical circuit, so we have the primary voltage V1, that is written over here. Where is that? This one, voltage V1, it is equal to EP plus ELP. So it will be equal to induced voltage plus the voltage drop in an leakage inductance. Since we have not considered here resistance, there will be one more component over here, that is the voltage drop in the resistance, because there will be some resistance which will be present, should be present in the circuit uh, of the winding. So that has to be taken into consideration, and that is considered like this. So the primary equivalent circuit will be now like this. We have V1, we have the voltage drop in R1, we have the voltage drop in X. L1, that is the leakage reactance of this, and then we have the voltage E1, that is the induced EMF in this winding. Similarly, for secondary, we have the voltage V2, we have, sorry, E2, we have voltage drop of E2, we have, sorry, XL2, that is the leakage inductance, and the voltage drop because of the resistance. So finally, we get the load voltage like this. So this is the semi-ideal uh, equivalent circuit of the transformer, because we are only considering the leakage reactance, that's leakage flux, and we have considered the resistance here. So here also you'll also find in the practicality that A is equal to N1 by N2, that is equal to E1 by E2. It is still equal to V1 by V2, because the difference between E1 and V1 is very small. We can consider them to be equal to, we can consider them to be equal. Same is the case here, but for the equivalency we have to keep it like this. Now this is the semi-ideal equivalent circuit of the transformer, because in ideal case we have assumed this to be 0, we have assumed this to be 0. But for why semi-ideal? Because we have to take care of the iron losses, and we have to take care of the finite permeability, because in case of ideal transformer we have assumed infinite permeability, and that means zero exciting current. But here we have to there will be some finite exciting current, because there will be finite permeability, and there will be some core losses. We have to take them into consideration as well. So in a transformer, the input current flowing in the primary of the semi-ideal transformer can be visualized to comprise of two components as well. So in earlier case, it was semi-ideal, it was only comprised of one component. So exciting current I naught, whose magnetizing component Im creates the flux, mutual flux phi, and whose core loss component II provides a loss associated with the alternating flux. So this we have already done in the no load operation of the transformer, where we have assumed that on no load the transformer charge a current of I naught. So this I naught comprises of two components. One is the perpendicular component, or we can say quadrature component, which is responsible for producing the mutual flux. Another is the in phase component, that's II, which is responsible for the core losses, that's eddy current losses and hysteresis losses. A load component I2, which counterbalance the second EMF, this N2 I2. So this is the load component of the current flowing in the primary circuit, that's why it is I2 dash. So it actually counterbalances the second EMF when current, when the load is connected on the secondary side, because it will draw the current, and that EMF will be equal to N2 I2. So from primary side it has to draw the current to counterbalance it, so that the total flux in this mutual flux will remain the same independent of the load. So that will be only determined by E1. Thus I1, that is the input current, will be equal to I0 plus I2 dash. So where I2 dash, as you know, will be equal to I2 dash will be equal to I2 dash by I2 is equal to N2 by N1. So this is actually that circuit which we have already drawn. In this case, exciting current I0 can be represented by a circuit model that we have already done. That's a parallel circuit. So that the semi-ideal transformer is now reduced to the true ideal transformer. Now you can see this is on the primary side. Primary side has the two current components. One is I1 and there is a I2. Where in series we have connected, that is R1 R2, because you will see that voltage E, that is actually responsible for these two current components. Here we have a voltage E that will be produced over here, because here we have assumed that R and X is 0, but here we are taking them into consideration. So the value of the responsibility of this II and IM is actually done by E1, not V1. That is why this circuit is usually connected between this point and this point, that is across E1, not across V1. So I hope you understood this. Now this is the corresponding equivalent circuit modeling that actually tells us the behavior of the real transformer. And here I don't show from here on we will not be showing the core because the core is also modeled as an electrical circuit over here. So in this case will not be showing the core over. This is the actual, we can say, practical transformer equivalent circuit where we have shown the primary resistance, leakage reactance because of the leakage flux. We have the exciting current that is required for producing the flux, and also that is responsible for the no load losses or the iron losses or the core losses. And we have this is actually the ideal transformer which we assume there is no losses there is no leakage, there is no magnetizing component of the current that is from here to here. So finally we have the secondary side reactances and resistances. So this will be the actual equivalent circuit of the transformer. Now these impedances, that is XL2 and R2, can be transferred to this side by the transformer ratio. As we know that transformers, this impedance can change to the here by simply multiplying by the square of the transformer ratio. Then they will be transferred to the primary of the transformer. So that is what we have done. The impedance R2 plus JXL2 on the secondary side of the ideal transformer can now be referred to its primary side or transferred to its primary side, resulting in equivalent circuit. That is this equivalent circuit. You can see we have transferred to them here, and we have represented them by x2 x dash L2 and R2 dash. This is I2 dash, this is V2 dash, where x dash L2 will be equal to N1 by N2 whole square into XL2. That is, we have multiplied them by the turn ratio. Similarly for R2 dash, it will be equal to N1 by N2 whole square into R2. And for this I2 dash, it will remain as it is, that is N1 by N2, N2 by N1 into I2. And for V2 dash, it will be equal to N1 by N2 into V2. So this will be here. V2 dash will be equal to N1 by N2 into V2, and I2 dash will be equal to V1 by, N2 by N1 into I2. This is the equivalent circuit. Now, this part is the ideal transformer of the part. We can simply neglect this. Therefore, there is no need to show the ideal transformer in the reduced transformer equivalent circuit to the T circuit. We don't actually require them. We can use this transformer to actually understand the behavior of the transformer, or simply we can see what type of transformer it is. Only this. That means then we can say this is the actual equivalent circuit of the transformer, which can be used to determine the performance of the transformer, but it is usually known as, since we have here them referred to primary, we can say this is the transformer equivalent circuit referred to primary side. While this V2 dash is not the actual voltage, it is equal to this N1 by N2 into actual V2. This I2 dash will be equal to N2 by N1 into actual I2. So this is how this can be modeled. This is, in this case, neglected. Similarly, the equivalent circuit can similarly be referred to the secondary side by transferring all the impedance, resistance and reactance of voltage to the secondary side. You can say we need to transform these impedances, current and this voltage to the secondary side. In that case, this will be Bm dash, Gi dash, this will be X L1 dash, this will be R1 dash, this will be V1 dash, and this will be I1 dash. When that is done, you will see that this is I1 dash, this is V1 dash, this is R1 dash, X1 dash, this is XL by 2. So XL2, R2, it will remain as its actual value, but these will change. So V1 dash will be equal to N2 by N1 into V1. I1 dash will be equal to N1 by N2 into I1. These are important. And G1 dash here actually should have been N2 by, actually this is R1, Ri dash, it should have been N2 by N1 square into Ri, but here it is admittance, so they will be multiplied by inverse of the transformer ratio, that is N1 by N2 into square into Gi. Bm dash will be equal to N1 by N2 into Bm square, but they will be multiplied as per the transformer ratio, direct transformer ratio. That is R2 dash will be equal to N2 by N1 into square into R2. X dash L1 will be equal to N2 by N1 square into XL1. So with this, we can get the transformer equivalent circuit referred to secondary side. So it may be noted that admittance, conductance and susceptance are transformed in the inverse ratio of the ratio squared in contrast to the impedance, which are already done earlier. That is direct ratio square. Let us try to do one numerical. It will be a little bit clearer to you. At 20 kVA 50 Hz 2000 by 200 distribution transformer has a leakage impedance of 0.42 plus impedance J 0.52. That means we have the resistance of the transformer 0.42 and the leakage reactance will be 0.52 in the high voltage side. This is the high voltage winding, that's on 2000 side, and 0.004 and J 0.05 ohm in the low voltage winding. Low voltage winding has this amount of impedance. When seen from the low voltage side, the shunt branch admittance Y naught will be equal to this. This is a shunt branch. This is Ri is equal to 0.002 and Gi is equal to minus 0.015 at the rated voltage and frequency. Draw the equivalent circuit referred to high voltage side, low voltage side, indicate all impedance on each circuit. Now on high voltage side, the high voltage side will be referred to 1, that's primary, and the low voltage side will be referred to 2, that's let us say secondary. So the transformer ratio will be N1 by N2, that's 2000 by 200, that's 10. Ratio is now equivalent circuit referred to high voltage side. It will remain as it is, and this will remain as it is because this is calculated from the high voltage side. Now we have to change only the low voltage windings. Low voltage winding impedance. This will be now multiplied by this voltage ratio, that is multiplied by 100. This will be multiplied by 10 square. It's multiplied by 100, and this will be sorry. When this is seen from low voltage side, the shunt branch. This is the value of the shunt branch side when it is seen on the low voltage side. We have to calculate it on the high voltage side. First, we'll calculate Z2 dash. We have to multiply it by the transformer ratio square, that is 10 square, that is 100, that will equal 0.4 plus J 0.5, that is shown over here, and then for the admittances we have to divide the same ratio, same square ratio, that is we have to divide by this. So it will be equal to 0.002 plus minus J 0.0 into 10 to the power minus 2, that is because of this. So this is the equivalent circuit of the transformer referred to primary side. You need not to show this ideal transformer 10:1. Similarly, we can transform these to the secondary side. We know that this we have to show this transformer on this side, and then we have to transform these values on the second side. These are already calculated on the low voltage side, so we don't have to change these values. It will be equal to 0.004 as given in the question. It will be equal to 0.005 J. This has to be divided by the 100, that is 0.0042. It will be equal to 0.0052, and this will remain as it is in the question. So this is the equivalent circuit of the transformer referred to the secondary side. Now you'll always see that the equivalent circuit, because of this parallel branch, it creates a lot of problem while calculating any current or power or anything else. So for the practical purposes, we usually use the approximate equivalent circuit. So what we do that in constant frequency of 50 Hz, power transformers approximate forms of exact T equivalent circuit that's commonly used. Okay, that we have just derived. With reference to equivalent circuit of the transformer, it is immediately observed that since the winding resistance and leakage reactance are very small, V1 is quite close to E1, even under the loading condition that we have already discussed. Thus, the exciting current drawn by the magnetizing current branch, that is this and this, would not affect significantly by shifting to the input terminals. That means, just a minute, this is the equivalent circuit referred to secondary side, or we can go for this primary side. Since we know that we have already told you that this V1 and E1 almost always remains equal to each other, we can say they are comparable to each other. So it is actually because this I naught is very small as compared to the load current. When I naught is small, and it may be of the order of 2 to 5%. When that is the case, you will see that the voltage drop due to this I naught in these R1 and XL is very small, and that is why practically or even during the load, you will see that the voltage drop is very small, and because of this I naught, which is already very small, you will see that voltage drop in this will be insignificant due to this this current. That means even if we keep it over here, or we keep it at this point, there will be very less difference in the voltages. And for practical purpose, we do it to save a lot of time, because there will be no difference, where there will be very little error while doing that, keeping this point at this point or this point, because we are actually introducing an error by moving this parallel branch to this point, but that error will be very insignificant. But by doing that, we are actually saving a lot of time, uh, which was consumed in solving the circuit. So that is one approximation, that we usually take this to this side, and then it becomes easy that R equivalent will be now equal to R1 plus R2 dash, and X equivalent will be equal to XL1 plus XL2 dash. They will be simply added. It may also be observed that with this approach, the current through R1 X1 is now I2 dash rather than this. So now, therefore, the current that will flow this R1 and R2 dash and L1 and XL2 dash, that will be I2 dash. It will not be now I1. Since I naught is very small, that I have told it is less than 5%. So this approximation changes the voltage drop instead. There will be not be any voltage change. So thus it is basically good approximation. It will save us a lot of time and a lot of computation processes that we may be using by keeping this branch at the middle of the front circuit. Now, the winding resistance and reactance being in series can be combined into equivalent resistance and reactance of the transformer as seen from the appropriate side. In this case, we have referred it to primary side. Remember that all the quantities in the equivalent circuit are referred either to the primary or secondary side, that's secondary dash, in the referred quantities, and suffixes one or equivalent resistance and reactance drop. After that, when we do that and when we understood that they are referred to primary or secondary side, we can then drop this ones, twos, dash, etc. We can directly see the equivalent circuit will be now like this. In computing voltage from the appropriate equivalent circuit, the parallel magnetizing branch has no role to play, and that can be therefore ignored in altogether. And that is the case, you can see when this is nothing to play here to calculate voltage drop at this point or this point or this point. You can see when we have shifted to this point, this V1 is applying to that point also. Whether it is there or not, always there will be the same performance of the transformer because we have the voltage V1 at this point. So that is why we, after doing this, when we have taken this to the primary side, we can neglect altogether the primary branch, and the transformer equivalent circuit will be reduced to this one. And in most of the cases, you will see that transformer equivalent circuit is used like this, ignoring the parallel branch, because it becomes easy to incorporate the transformer in the circuit and solve it while neglecting the parallel branch. In fact, some system studies, a transformer may be represented as a mere series reactance as shown in bigger figure like this, because resistance is very small as compared to reactance, and we need sometimes we ignore the resistance as well. This is a good approximation for a large transformer which always have a negligible equivalent resistance compared to equivalent reactances. For large transformers, you will see that their resistances will be very small as compared to reactance, and we can neglect them. And this model is almost always used for the fault analysis in transmission system. For fault analysis, the transformer is simply represented by as mere reactance, not the resistances or the parallel branch. There will not be like that. But in most of the cases that we use, we'll be using it like this. And this will be the exact transformer circuit. That will be this. Now let us try to do one numerical on this. We have a 33 kVA 220 by 2200 by 220 50 Hz single phase transformer that has the following parameters. Primary winding, that's high voltage side, we have R1 is equal to 2.4 ohm, leakage reactance X1 is equal to this. Secondary side, we have resistance is equal to this, and leakage reactance is this. Find the primary resistance and leakage reactance referred to secondary side. We have to refer them to secondary side. Find the secondary resistance and the leakage reactance referred to primary side. Find the equivalent resistance and equivalent leakage reactance referred to primary or secondary side. Calculate the total ohmic losses at full load. Calculate the voltage drop to be supplied at the high voltage side in order to obtain the short circuit current, that's 160 amperes in the low voltage winding. Under these conditions, find the power input also. This is very simple. First we will calculate this. After that, when we assume it a circuit, a simple electrical circuit without a parallel branch, it becomes very simple. First, the primary resistance refer to secondary side. Since secondary resistance will remain as it is when we refer it to secondary side, we need to refer primary to secondary side. That will be equal to R1 into N2 by N1 whole square, where N2 is now this 220. We have to refer it by 220 side. This will be 220 divided by 2200 square. This should have been square. Actually, it will be 1 by 10. That is equal to 1 by 100 1 by 10 square, that is 0.024 ohm. Similarly, for the leakage reactance, it is 6. When you divide by 100, it will be equal to 0.06. So this will be the value of the primary resistance, primary reactance referred to secondary side. So referring the secondary leakage reactance and resistance to the primary side, we have to multiply them by this transformer ratio. Now it is 2200 divided by 22 whole square. It will be equal to R2 N1 by N2 whole square, that is 0.03 into 2200 divided by 220, that will be into 10 square. It will be multiplied by 100, that will be 3. For this case, it will be 0.07 into 100, that will be 7 ohm. This is the referring on the primary side and the secondary side. Find the equivalent resistance and equivalent leakage reactance referred to primary or secondary side. Now refer to primary side. Refer to primary side. Refer to secondary side first, because this is the part we calculate. Refer to secondary side. So primary side resistance is refer to secondary side, that is 0.024 plus 0.03, which is equal to 0.054. And for leakage reactance, 0.07 plus 0.06 will be equal to 0.13. Similarly, referring to primary side, so we have 2.4 plus 3, that is 5.4. We have 6 plus 7, that is 13. That is what we have done over here. So equivalent resistance on the, it will be equal to this. Refer to primary will be equal to 2.4 plus 3, that is 5.4, and this is 13. That will be equal to R1 plus R2 0.54, and XC plus H will equal to 0.13. So this is actually this refer to high voltage side resistance. Equivalent circuit. This one, and we are using this, and after that it will be very simple. Now the primary full load current, that will be equal to, the primary full load current will be equal to 33 kV divided by 2200, and secondary full load current will be equal to 33 kV divided by 220. So the primary full load current will be equal to 33,000 divided by 2200, that is 15 ampere, and secondary full load current will be equal to 150 ampere. They are related by the term ratio again. So Ohm's law at the full load on the primary side will be equal to, or we can say we can calculate it on the equivalent circuit. You can see we have the equivalent resistance on the primary side. What is that? That's 5.4, and we have the current when we refer it to this high voltage winding or primary side. It is 15 square into 5.4, that is 1216 watts. Or we can do it for the other way around, that we have referred to secondary side, and we have to calculate, we have to multiply this square to the total resistance referred to second side, that's 0.054, that's this. We'll again get the same value. Now the last part is calculate the voltage to be applied to the high voltage winding in order to obtain the short circuit current, that is 160 amperes. So we have to here when we short circuit it, a 16 ampere would have been we can say flowing through this circuit. So total voltage that is to be applied from here will be the voltage drop across these two, we can say RE1 and RE2. So if 160 amperes in the low voltage winding is equivalent to 116 amperes in the high voltage winding, you can do that as well, because 160 amperes in 0.054 plus 0.13 ohms, and you can use 160 amperes here. Since it has shown the it referring to high voltage winding, so it first converts that short circuit current on high voltage side by the transformer ratio, it will be 16 amperes. The equivalent circuit of the transformer is shown like this. From the equivalent leakage reactance will be simply 5.4 plus G13, and the total current, total voltage that is to be applied from here to so that this voltage, this current will be flowing through this, that will be equal to 16 ampere multiplied by this impedance, that is this impedance will be 14.08, calculated like this, that is 225.28. So power input will be in this case, because power input is to be calculated, that will be only that is consumed by this resistance, that is 16 square multiplied by 5.4, that is 16 square multiplied by 5.4, that is equal to 1382 watts. So power input can also be calculated by the VI cos of phi. V is this, I16 cos of phi will be equal to 5.4, that is R by Z divided by 14.8. It also comes out to be same. So with this, I hope you have understood it. I will stop for it. Thank you.